At this point, you've probably been doing a lot more math than maybe you thought you would, and hopefully it's not too scary for you. I wanted to talk about a few different mathematical concepts that we could play around with, and we'll add, maybe a little bit more functionality to what we're doing. The three things I'm going to discuss here are modulus, trigonometry, and Perlin noise. So let's look at these a little bit more closely. So we've actually already used modulus in the previous video. We used it kind of to create a timer as a shortcut to do it. When you see this percentage sign, that's how you know we're using this concept modulus. It basically calculates the remainder when one number is divided by another. So here's some examples. 5 modulus 5 is 0, the remainder is 0. 5 modulus 4, the remainder is 1, and so on and so forth. So using this or using this relationship, you're seeing this as number increases, we can actually create or use this to drive some form making. So here's an example. This is some code I've already written, and you can see I have a sketch. The size is 400. I have a background, a black background, and I'm drawing the circle onto it. It's in the center of the sketch, and what I'm doing is I'm using frame count. Again, frame every time a frame is run, or every time the draw is run, you can think of it that way. It's adding to the frame count, and by doing a modulus of 400, where the biggest this can ever be is 399 as the remainder. So it's going to give us a circle that's almost as big as the size of the canvas. So let's take a look at what that looks like. It starts off small, and then it gets bigger. And I haven't actually done that much code, but you can see that if all I wanted was to kind of increase the size of something and then make it reset, this could be a shorthand way for me to do it. We've looked at other ways to do it using like speed or if statements, but this might be another way to approach it. So trigonometry is also something that maybe we have some fear and trepidation around, but I think there's ways to use it painlessly in processing and programming. We've used it before to drive the size of forms, or also kind of the movement of bouncing balls. Again, this might be a little bit of review, but I wanted to kind of talk about the functions that we can use and we can leverage in processing. The sine function, now with sine and cosine, they always return values between -1 and 1, so that's helpful. We just need to multiply it to get like a greater I guess a greater range, and the movement of these waves is wave-like, right? It's smoother, so that gives us a more organic kind of motion. And tangent is something we can use. Now these are technically all have to do with relationships between the sides and angles of triangles. I don't think it's that important to know that. I think it's important to know how these functions operate and how you can use them. So tangent, let's look at these, what these functions look like. You can see again the wave-like function of sine. Cosine is a similar wave, but offset a little bit. You can see it's kind of shifted. And then tangent is this, it's got a curve, but it goes, the range is sort of like -infinity to infinity, which we can leverage. It starts really small and it gets really big if we're going from left to right. Let's take a look at what those things look like. Here is a sketch that I've made using trigonometric functions to control movement. You can see the first one is using the sine wave. It's an ellipse here, and it's off to the left. The height is being modified by sine theta times psi 0. Now psi 0 is that sort of scale, kind of like a scale value that's going to make it jump up larger than -1 and 1. And then we have cosine in the center, and on the side you're going to see what does it look like if we use tangent to drive the vertical position of this circle. So you can see we have sine on the left, cosine in the center, and those are moving within a limited range, whereas this tangent is going, it's starting like, really negative. So it's really high up, and then it's going really positive. And you can see it slows down as it gets to the center, and that is, you can see that reflected in the wave or the graphic, the plot of it. So that might be something too, if you just want something to kind of move onto screen and then move off, maybe you can leverage the tangent function there. Okay, and the last thing we're going to look at is Perlin noise, which is a really helpful way to create smoother variations. We've looked at randomness as a way to kind of make values change, generatively. The problem with that is it's often a kind of jagged, kind of irregular. Perlin noise produces a more natural, ordered sequence of pseudo-random numbers. It's something that was pioneered by Ken Perlin, who was, an early computer graphics artist and someone who wanted to make like procedurally based organic textures, things like wood or marble. They have kind of a natural flow to them. So these are, forms like these are maybe things that would benefit from using Perlin noise versus randomness. And let's take a look at what that looks like. We're going to start just by writing a sketch in here. So we have a void setup and a void draw. And we're going to start, with noise, we're going to need to feed it a value and then increment it, just kind of like the trigonometric functions like sine and cosine. So we're going to start with a float t, and we'll just set it to 0. And an increment here. Let's say the increment is something small, 0.1. Now, if there's a larger increment, we'll see a large, sort of a greater variance, so more jumping around. But if it's smaller, we'll see kind of smaller leaps and jumps. Okay, so we'll set the size here to 960 by 540, and let's turn the frame rate low so we can see kind of the output and observe the differences. We're going to do a white background here, and we'll make kind of like a line graph. So we'll start with begin shape, and we'll do a for loop. We'll basically go from left side to the right side. So we'll start at 0, while I is less than the width, or we can say less than or equal to, so it goes all the way across. And let's say I, instead of plus plus, maybe we'll just say plus equals 5. So it doesn't need to do every single point, but 5 pixels is pretty small. And then we'll set a vertex here, which will be I, that's the X value. This one we'll put towards the top, maybe starting at height divided by 3. And let's this is the random line that we're going to make. So what we'll do is we'll write random 20. This will give us a result between 0 and 20, right? So we'll see what the random function gives us if we give it a range of 0 to 20. And after all of this, after the for loop, we want to just end the shape, and that will kind of connect it together. So then the next thing we're going to do is make a line, a similar line, but it's based on using noise. So we can set it up the same way, begin shape, and I'm going to take the same block of code. I'll write it like this, but now on the vertex, I'll make sure that I change it a little bit. And I'll start at height divided by 3 times 2, so this is 2/3 of the way down. Instead of plus random 20, what I'll do is I'll use noise, and I'll feed in that value t. Now noise always returns a value between 0 and 1, so if I wanted to have the same range as this, I'll just multiply it by 20, right? So we're taking the sort of smaller value and multiplying by 20 to give us kind of the same amount of ups and downs, or the range, like I said. Okay, and then just like theta, if we're doing a sine or cosine, we're going to add the increment here. And let me also just print this out. What does noise t look like? Or, I mean, I guess I just to kind of see. I mean, I guess I could have put that here. To, one is going to this is going to be before the increment goes in. The other one's going to be after. Okay, so let's clean that up, and then let's remember to add end shape. Okay, so let's run that, and we'll see the difference. Okay, so you can see the line on the top is using a randomness between 0 and 20, and you see that that's more jagged. It's just kind of jumping up and down. The frame rate we set to 4, so that's why it's going kind of slow. And here you can see that the value kind of changes in a smoother, more organic fashion. Let's take a look at that, what that looks like. And remember, if I change this increment to be much larger, let's do it at 0.5, you should see it becomes a little bit more jagged. Yep, right? So knowing this, we can fine tune the increment, and also using noise get a sort of more controlled result. If I make it even smaller, this is 0.01 increment, you can see the difference. It's a much smoother line again. So this is a good illustration of the differences between randomness and noise in processing. Okay, so let's take this idea of using noise and use this to drive some of the motion in a sketch. I'm going to make a pattern of circles, and I want to, instead of using randomness to drive the size of those circles, I want to use noise, and this will again give me a smoother, kind of more natural type of movement or motion. So we'll do the same sort of thing that we did earlier. We're going to set up a t to feed into the noise function. I'm going to set up an increment is equal to 0.1. And again, what I'm trying to do is make a series of gridded circles and let the noise drive the size of those. So let me start with a dark background 5. I don't want any fill on these. Let's now we can adjust the increment here, or we could say plus equals increment. There we go. I mean, I guess I could do it here, or I could do it after I draw this grid of circles. To do a grid, like a pattern grid, we're going to have 2 nested for loops. So let me start with I equals 0, while I is less than or equal to the width. And then, how far do I want these things to be spaced out? Let me say 60 for right now. Okay. And then we'll do another nested for loop to make this 2 by sort of a grid. So J, in this case, we'll do height because this is going along the vertical axis, and then we'll do J plus equals 60. And again, open and close the curly braces, and here we will throw in the ellipse I and J for the X and the Y. And yeah, we can use noise T. Again, noise will give values between 0 and 1. So if we want this to actually get kind of big, maybe we'll say 60 because that's the size of the spacing in between the grid. So this should give us times 60. Yeah, this should give us some variation there. And let's just run that. Let me make sure that is good. I did Command T to clean up the code. That should be good to go. There we go. So this noise you can see is affecting all the circles, because you can see T is the same for all of them, and it's moving in a sort of smoother motion. If I made this 0.5, we're going to see even more variation. It's going to see like a little bit more poppy. If I wanted less, I could do 0.05. So let's see, this should be a lot smoother, right? So again, we're not really animating anything. We're letting the noise drive this, and it kind of looks like it's live and it has its own motion. From here, maybe I'll think of ways to, maybe I can use the fill here and start to bring in some of the noise. Maybe I'll take noise T and multiply by 255. So as the noise gets larger, this red value will get bigger. We could try some other things here, or I could say plus I times increment. So this is a way of using like the I value to change, create a gradient here, and maybe we'll multiply that by 255. So I'm just messing around and trying to think of ways. I guess, I could do the same thing here, or maybe I'll just do time J times increment. So it shifts everything over using that J value, which is it's the Y value. Okay, and I think that should do it. We've added some code here. Yeah, there you go. So there's we've used some noise here, and you can see as it gets bigger, the colors also get brighter, right? So we're trying to maybe make some relationships in the code, thinking about how those things might all interact. All right, in the next example, I want to show, we'll take this idea, but we'll make it so that each of these circles is working independently. Right now, they all get big at the same time. So we're going to try to do this using two-dimensional arrays, which will be another good technique, and it will allow us to have these all operate independently. Okay, so in order to do something like the previous sketch, but make each circle independent, I'm going to need to rewrite some classes or write some classes here, so that each of these circles will independently pulse using noise. So the first thing I'll probably do is go and build that class out, and then we'll go and make that grid pattern, and we'll do it using a two-dimensional array, which will look similar. We're basically going to have to do is use nested for loops, or use nested loops again, to create that grid of circles. So let's go ahead and start writing what that might look like. Again, I'm going to write a class, and maybe I'll call it pulse, because it was kind of pulsating. So I can choose the name for that. Let's throw in the data. We need a float x, float y. We need a diameter here, size. We're going to do noise, so we'll need that kind of value to feed into it. Let's also feed an increment, and maybe we'll throw a color in there as well. So this is the data that we'll be using. Then we'll create the constructor, which will pass those things over. Okay, so it'll be like this, pulse, and we will throw in these temp variables. So float temp x, float temp y, float temp diameter, float temp t, float temp increment. The last one I think was color, so make sure we specify the color temp c. I think that is all of it. Down in here, we're just passing the variables over. Y is equal to temp y. Diameter is equal to temp diameter. T is equal to temp t. Increment is equal to temp increment. Did I write increment in that past one? Okay, I did. Good. And then we said color. C is equal to temp C. Okay, I think that is good. Now we want to write our methods here. So kind of what we did before, we'll make our own function. We'll call it run. You could call it, whatever you want. The fill will be C. I think the styling we used was like no stroke. And then we had an ellipse here that we'll say is at X and Y. we'll use diameter, but this time we'll add noise t. And we can multiply it by diameter, so that's going to give us a range that, again, noise will go from 0 to 1. So this will essentially, it could double the size of it, or it could, if noise is 0, then it'll be the same. So I'll just take this, copy and paste it. I could have done circle here instead. Maybe I should start writing it that way. It's more efficient, but it's an old habit. Okay, so the other thing I need to do is I always need to increment it just like we did with theta. Otherwise, the value will never change. Let's see, that ends there. And then all of this is inside of this class pulse. Okay, so that looks pretty good. Okay, from here, I'm gonna, maybe I'll set things up first, and then I'll go and make the two-dimensional array. So let's do the size again, 960 by 540. I think the background, we had like a black background or something close to that. I'll just do a black background for right now. And yeah, I think this will be okay right now, just to start. Okay, so what does a two-dimensional array look like? Well, it's basically so we want to specify what's the type. Pulse, we're going to use this object pulse that we created. Instead of just doing one set of square brackets, we're going to do two sets, so it's a two-dimensional array. This allows us to kind of hold things, again, think about like that grid of circles, some that are going in one axis and some are going in the other axis. I'm gonna call the array grid, and this is a 2D array, and this is, I guess this is us declaring it, so it's a declaration. Now we need to we can set the size of this. How many are in each one? So you want to think about how big is this grid, how many of these are in each one. Because I want to maybe make this adaptable, I might make some variables here, columns and rows, and feed those into that for the length. So this is just declaring it, and I need to create them. So I'm going to write. I guess I could have written this all in one line, but I'll just write it down here. So I'm going to say, let's make a two-dimensional array that has 10 columns, because I've set that to 10, and 10 rows. So this is, again, we always have to set the length of an array. Okay, that looks pretty good. Again, we're going to have to go and use loops to create these. So I'm going to use I again. I'll say, while I is less than columns, calls I plus plus. Whoops. Okay, so that's one for loop, and inside of here, nested for loop, we're going to have another loop while j is less than rows, right? So the vertical and the horizontal axis, and j plus plus. Okay, so this is how we're going to feed or initialize the array. Okay, so what we'll do is instead of we'll use the array name grid, but now this grid has two indexes, like it's a 2D array, so it needs both one index number here and another index number here. So we're going to use I and j, and again, just like creating a pattern, a grid, we're gonna set it up like this, and then we'll create a new pulse. So here we declared it, here we created it, here we're initializing it with values. Now the pulse that we created takes x, y, diameter, t, increment, and c. So let's give it some values here. Now, if I wanted to evenly divide the rows I could, let me just go in here and I could make two variables, or I could do the math. What's the size in between the columns? It would be, I'm thinking about the horizontal spacing. It would be width divided by columns. That would give me an even distribution across. And I could even say float y size. This would give me, let's say I could do height divided by rows. That would give me an even distribution of the vertical spacing. So I could have just done the math and put it in here, but just to clean it up a little bit, I'll say, well, let's take I times x size, and let's see, yeah, we'll start with that, j times y size. So this is going to give me evenly distributed circles or pulses. So those are the x and the y values. The next one was diameter. Okay, so what is our diameter? We can throw in a number 40. I mean, I could also put in x size. Maybe that's something to try. But I'll just put in 40 for right now. And for the temp t, really what you want with t is, if you want them to start at different values, you just want a different number here. So I could put in I or j, or put a random number if I wanted to. By putting in j, it's gonna they're gonna be offset, which is fine. The increment, now, if I want them to all be the same increment, I could, moving at roughly the same type of speed, but maybe starting at different values, I could do 0.1, or maybe I'll do a random value, random 0.1, so that some are moving faster and some are moving slower. And I think the last one was my color here. So, you know, why don't I make a value to pass into it, a variable here. So color C is equal to, so yeah, we could just throw in a random color in here. Maybe this one has a little bit of a range to it. Random 200, 255. You could try throwing a map function in here, and maybe it's a gradient across the x or y axis. I think that let's see, is that enough? Maybe that's one extra. Oh, whoops, I didn't put in that color C, so there we go. Color C, I think that's good. Sorry, I gotta make my screen a little bit wider. The code is getting long. Okay, clean that up, and let's call this function. Now we've initialized it, and inside of here, let's just go and actually call this. Whoops, I wanna make sure, hold on, 1, 2. Okay, so that's inside of there, that's inside of there, and okay, so this is the nested for loop, and we'll call it up grid I, j, and then the function that we're gonna run is run. We've defined that down here, run. Okay, will this work at this point? Okay, so yeah, you can see that it's running. There is, some of these are moving faster than others. This is a random distribution of colors. One thing I'm noticing is that because I started at I think it's starting along here in the zero in the x and then y. If I wanted to shift it over a little bit, I could just take the diameter or take the spacing divided by 2 and then just shift it over. So I might do that in my code down here. Maybe I'll just say plus. Well, actually, or you know, I can either do it down there, or I can do it when I feed in the numbers up here. So maybe I'll do plus x size divided by 2, and then I'll do plus y size divided by 2, and that should just shift everything over. There we go. So it feels more centered in here, and we have this kind of random color set up. If I wanted to do, maybe while we're here, we'll just do mess around with this. We'll do a gradient. What if we wanted to map this? I could take map of I. So now I'm using the I, which we're kind of using as a marker of the horizontal position. I will go from 0 to, I will go from 0 to calls. That's the maximum, right? And we can remap it 0 to 55. Okay, that's 1. Then maybe we want to remap J, which will it starts at 0 and it goes all the way to rows. That's the current minimum and maximum, and then the new minimum and maximum. We could go 0 to 255 again. Okay, and then maybe 0 to 255, comma 255, and then the last one maybe we'll do I plus J. The minimum is 0, and then the maximum would be rows plus calls, and then maybe we'll go in the opposite direction, 255 to 0. So we're remapping these values, and I think that should just give us a kind of a gradient across. There you go. So it's like a color gradient. Yeah. So again, we're using the same structure, sometimes building it out differently, initializing it in different ways. You can get really different results. Okay, so for this assignment, I'm curious to see what you make using noise to drive some of the visuals. Again, it'll be a more organic or smoother kind of motion or reaction versus randomness.